Welcome to the lecture on the virtual and physical address space of the Linux operating system. So we will start with looking at the kernel's virtual memory and the overall virtual memory map of any process. So Linux has two virtual memory addressing modes. One is a 48-bit and the other is a 57-bit address. So we will use the 57-bit address scheme because it is bigger and it is more generic. So 57 bits is equal to 2 to the power 7 multiplied with 2 to the power 50. That's the size of your address space, which is 128 into 2 to the power 50. So 2 to the power 30 is giga, 2 to the power 40 is tera, 2 to the power 50 is peta. So it is 128 petabytes. Out of that, 64 you give to the user space process, which is again a lot of virtual memory, but fair enough, you go ahead and do that. The remaining part, which is 64 petabytes, is kept for the kernel, 50-50, half-half split. So there you assign different regions and you also keep holes or spacings between regions, such that in case a region wants to grow or something, it can, but also you can use it for correctness purposes. In case there is a bug, it will start infringing into these inter-region spaces. And nothing should be here. In this space, nothing should be there. So it's possible to find that. So out of the 64, a noteworthy region is the direct mapped region. So let's first look at it in a simple term. What if my virtual address is equal to my physical address? In the direct mapped region, assume that my virtual address and physical addresses are the same. Then this is tantamount to accessing the memory directly. All right. So this is because you will always have translation. The processor doesn't know whether you want to use translated memory or untranslated memory. But if you have deliberately set the mapping to be the same, that is virtual is equal to physical, you can access the memory directly. That is why this part of your virtual memory map is useful for that. But as you can see, this part does not start from 0. All right. So if it does not start from 0, then the relationship is slightly different. It is basically your virtual address, which can be something like this, minus some offset. Is your physical address. All right. So they are not equal, but essentially they are offset. So there is an additive factor. So it is still very easy given a virtual address to compute its physical address and vice versa. And you will directly come into this direct mapped region where any memory address can be accessed at will, which is anyway the kernel's job. Also, the other thing is that you would like to keep many structures such as the page table in a reserved part of the physical memory and access it directly based on its physical memory address, or the virtual memory address where there is a fixed offset between them. Again, this is tantamount to the same thing. In all of those cases, they are stored in this virtual address region that allows you to very efficiently access physical memory where the mapping is clearly known. So this is more or less equivalent to accessing physical memory directly. It's just that there is a constant offset, but that's not a big deal. And anything starting from any system-wide table to page tables, where you do not want to use virtual memory, you don't want the risk of page faults, you want to pin those pages in memory and access them directly, use this region. For memory mapped I/O, 12.5 petabytes are given because you may have large device address spaces. The per CPU area has actually 500 GB, which is a lot. And we have already seen the benefit of this. So of course, we did not use a lot of area. We just stored small fields. But you can store a lot of data in this per CPU area if you wish. The kernel code per se is quite small actually, 512 MB. The kernel code is per se very, very small, half GB. And a large part of the code, which is in modules, and all the device drivers and so on are in modules, they are loaded on demand. So they are loaded and attached to the kernel on demand. So these are known as modules. But this 1520 MB is not a part of the kernel unless you want it to be. And that too, it's a very small subset of this is going to be a part of the kernel. Okay. So normally what is the convention is that when you are booting, you go to your storage device, or let's say you go to your memory, and the kernel code starts at physical address 0. That is your convention. That is how you boot an operating system, because that is where it will start from. Either it is physical address 0 or some known physical address, which is like a fixed offset, and you start from there. So let's look at the page table. So if you would recall, we had an struct inside every task struct. That has a pointer to a page table. A page table is called a page directory in Linux, and the pointer is pointing to the base address of the top level page table. The CR3 register also points to the base address of this top level page table. So what we are doing is that we have 5 levels of paging in Linux. So we looked at 2 levels way back in chapter 2. So in chapter 2, we looked at 2 levels. In chapter 5, we'll look at 5 levels, because we have matured, right? 2 has become 5. So what happens is that your page is still 4 KB, 12 bits. Then the remaining 45 bits, because 45 plus 12 is 57, the remaining 45 bits are split into groups of 9 bits each. So 9 into 5 is 45. And the first one is just an array of page table entries. Then the middle directory, upper directory, 4th level directory, and global directory. So they have names: global directory, 4th level, upper level, middle level, final level. And in each page table entry, along with the translation, which anyway has to be there, and also information whether this is there in memory or not, in swap space or which device, there is additional information regarding the permission of the page. And we have heavily used this, mind you, to track accesses and so on. So you can give it read permission, write permission, execute permission, permission for atomic operations to be executed on this page, and none, which is the one that is actually used for marking it as not accessible. The moment you mark it as not accessible, whenever there is, so this has to be propagated to the TLB also, because the TLB is the one that checks. The page table just maintains a backup. So that the TLB says it's not accessible, you have a soft page fault, and you come here. And if you see it was deliberately induced to track accesses, you will revert it. So we will look at the follow PT function, which is the way that you traverse the page table. And this, arguably, is very important in the context of Linux, because traversing the page table is a very, very key and important activity in the memory system part of the overall kernel. So the code is not hard to understand at all. You have a pointer to a page global directory, 4th level, upper level, middle level, and the final page table entry. So what happens is that from the struct, you get a pointer to the page directory. The page directory goes here. From the page directory and the address, you extract 9 bits. These 9 bits are which 9 bits? They are 49 to 57. And then you get a pointer to a 4th level directory. From there, a pointer to from there a pointer to the upper PUD. From PUD, a pointer to PMD. From PMD, you get a pointer to the actual page table entry. Right? So essentially, it's just a walk, and you can easily see the way that this walk is happening. Now, what normally happens is that when you are providing the final page table entry, you also provide a spin lock along with it, and you lock the entry and you return a locked entry. Why is this being done? Because in general, when you will access a page table entry, that is a shared structure, right? So you will access it inside a lock. So why get the entry first and then lock it? Why not do kind of combine both? That when you're getting the entry, you get it in a locked state, you use it, and then you unlock. So this is kind of like a shortcut. So finally, you return it. So far, so good. So the rest is easy to understand. Why this is a double pointer should be clear by now. We have discussed a fair amount of pointer concepts in arithmetic. The reason is that in this case, what do you want to return? What you want to return is a page table entries pointer. That is what you want to return. But you are returning int because that is the status of your operation. 0 means all good, non-zero means something went wrong. So how will you return? Standard thing, you send a pointer to whatever you want to return, it will put it over there, fill it and return it. This is a standard trick that we have been seeing, which is why you have 2 pointers over here. Now let us look at the way that, let's say, the PMD is accessed. Right? Let's just look at one level, so you will quickly appreciate. It's not very hard at all. So how will you access the PMD? You will have a PUD entry, right? That will have a pointer to a PMD table. Then you will compute an index that will lead you to an entry, right? That entry is your PMD entry, correct? So the key idea is that, so my input would basically be the PUD data structure in the table of PUDs. So that is my first input, and it's an unsigned long address. That's my second input. What I do is that I take this quantity. This quantity is nothing but the base address of my PMD. So let me write it down. Okay, this quantity is the base address of the PMD, and this quantity is the offset. Is the offset within the PMD. This quantity is the offset, and clearly whenever you are doing pointer math, you understand that the units etc. will be changed, right? So if let's say I'm adding 5 to a pointer, you're actually not adding 5. You have to look at the data type of what that is pointing to. It will be 5 times size of that data type. So this we have seen. So let's say you're adding 5 to int star, you are actually adding 20 because the size of an integer is 4. If you're adding 5 to a double star, you're adding 40 because the size of a double is 8 bytes, right? That is what you're doing. So this part is clear. So let us look at them individually. PMD index takes the address. It needs to right shift the address by some amount. What is that amount? It's bit number 22 to 30 is what you want to extract. So you'll right shift the amount by 21 positions. That is what you will do. And then you will basically compute an AND with 9 bits. Pointers per PMD is 512. So this is 512 minus 1, which is 2 to the power 9 minus 1, which is 9 ones. So you'll compute an AND with this, and then you'll extract bits number 22 to 30, which will go over here as the offset. And because you're adding an offset, the pointer math will take care of the rest, including doing that implicit multiplication, which I was just talking about. PUD page table, on the other hand, its return type is a pointer to a PMD table, which you can clearly see it is returning. How is it returning? So what it is doing is that it is taking PUD val PUD, which is nothing but the address that is stored in this entry, and ANDing out its lower 12 bits because you want everything to be aligned to page boundaries. So normally what happens is that Linux does not like to waste space. Whenever there is a little bit of space, it will fit a few bits there, right? So this is how stingy you are in the kernel. And in case, let's say that there is some variable, but some bits are not needed. In the sense later on, they will get ANDed out to become 0. It's a good idea that you use them to store a few bits. That is exactly what the kernel does with a few additional bits of the PUD address. Which bits are those? They are bits 1 to 12, which you will convert to 0 because all addresses are aligned to page boundaries. That is exactly what you do. You do it. So this quantity is basically 2 to the power 12 minus 1, which is, sorry, it's not this quantity, it is the logical inverse of that. So 2 to the power 12 minus 1 is all ones. In positions 1 to 12, you compute a knot of that, then it is all ones and then all zeros, you're ANDing it with this. So here you're using the underscore VA macro, which, if you would recall, is actually going into the direct map region that we just discussed, right? So the underscore virtual macro is taking the physical address and adding the page offset. The page offset is nothing but some sort of an offset into the direct mapped region, right? So basically this, let's call this the page offset, where let's say all your page tables are stored. So whatever you are adding on top of this, the underscore VA macro basically returns this value. All right. So what you store is, think of it as the physical address. The physical address is being added to that offset which is inside your region, and then that is being converted to a virtual address such that the kernel can then access it. Right? So far so good. And that is because of this direct map region, as we said, it is shifted by an offset. So the structure of a PT entry is like this, that the frame number can be 52 bits maximum. That's how much Linux supports, right? And that is obvious because it is 52 plus 12 is 64, that is fine. Then we have protection bits. We have already seen what they are in a previous slide. So your protection bits are there. And we are clearly differentiating in this case between a frame, a physical page, and we'll introduce a new term, folio. So a frame is a 4 KB region in physical memory, that's all. But what is stored there is actually physical page that is stored there. So what happens is that a modern program can have billions of physical pages, it can be huge. If that is the case, it will require too many address translations, page table entries, TLB entries, so on and so forth. It's a wiser idea to create groupings of 2 to the power n physical pages. So create groupings of, let's say, 2 to the power k physical pages, which are contiguous in both virtual memory as well as in physical memory. Then what will happen is you will maintain a single entry for this entire group, and you will try to leverage hardware support for having a single TLB entry also. We'll discuss that in a second, but let's call this a folio. So folio is 2 to the power k physical pages, where or 2 to the power k virtual pages, which are contiguous in both the physical address space and virtual address space. So again, now there are mild deviations and nuances to this idea, but let's not go into that. This is a good definition to work with. All right. So the struct page is a key structure, and of course the folio kind of expands on that, but let's look at a struct page. So for every physical page, we have a struct page, which will obviously have its physical address. Along with that, it will have a lot of additional information, which means every page in memory is associated with a struct page, right? And that will have a lot of information, such as a pointer to its address space, like is it a normal memory page, is it an IO page, or is it something that DMA is going to write to? Some idea of its linkage. Sometimes what happens is, if you are reading a file, you take a large number of pages and start mapping them to addresses in a file. Is it part of that? Is it part of a pool of pages? Other things. And then finally a reference count, which is a standard pattern that we are seeing in the kernel. Reference count is how many entities in the kernel are pointing to you. When this reference count becomes 0, the page can be garbage collected. In the sense, the data structure can be freed and its space can be reclaimed. All right. So it's a very flexible data structure in the sense there is one massive union, because there can be pages of many different types. Regular pages, IO backed, file backed, DMA pages, so on and so forth. A folio has 2 to the power k pages, and typically you point to the first page of this compound page and then you say how many pages are there in a folio, right? But he'll point to the first one. Because you have contiguity, it's kind of helpful. A folio is quite useful when you are dealing with large pieces of data. Consider a file or a memory map file, things like that. A folio is super useful. Also, because it is contiguous, there are advantages in terms of prefetching. So, a hardware prefetcher is basically a circuit that looks at your sequence of accesses or sequence of misses and guesses what you will access in the future based on past accesses. It's like doing machine learning. So, if let's say you're accessing a folio and you know that this entire thing will be accessed and they are in contiguous regions, it's very easy for the prefetcher to find out that I am here, but I will access all of these addresses. So, they can be brought beforehand to the upper levels of memory. They can be added to the page table and TLB beforehand. That will increase your performance substantially. So, in the current version of the kernel, people are thinking more in terms of folios as compared to pages. So, the folio is fast replacing the page and the folio is becoming an atomic unit. Any statistics like LRU statistics and so on are modified, you maintain at the folio level as opposed to the page level. So, as we speak, this transition from a page to a folio is happening mainly because of scalability concerns. If you would see, life has a weird way of kind of looping back. Initially, we were using base limit, which was contiguous in both the virtual space and the physical space. Then we said a lot of problems are being created because of holes, and holes are also called external fragmentation. So, we went to paging where a virtual page can be mapped anywhere. Now, we are saying that there are too many pages, managing them is difficult. So, let us again create a contiguity, continuous match between the virtual address space and the physical address space. So, again it comes down to sort of going slightly back, which is why folios are there. So, we will look deeper into the definition of a folio. So, a folio presents itself as a page in the sense the atomic unit for a large part of the memory management subsystem is actually a folio now, and it's not a page. But as I said, a folio is a set of 2 to the power k pages. It presents itself as a page where basically the page is the first page of the folio, and then you have a range, the number of pages in the folio. So, a folio has a permission. All the pages in a folio share the permission state of the folio. It has a copy on write state, which means that upon a fork, the entire folio is copied. If a byte is written, then a new copy of the entire folio is created. So, whatever page, so whenever there is a need for migration, swapping, replication, everything happens at the level of a folio. So, Linux is a software solution, and whatever you make has to be compatible with diverse kinds of hardware. Not just one kind of hardware, but many kinds of hardware. So, what happens is that in some cases, there is a facility for creating a huge page. A huge page is a hardware level concept and a folio is a software level concept. But often it is possible to marry both if there is hardware support, correct? So, the notion of huge pages kinds of aligns well with the notion of folios. And let's look at what is a huge page. So, the main reasons or the main problems that are motivating the design of a huge page are like this, that a modern process has a lot of pages, right? Its memory footprint is very large. If the memory footprint is very large, you need a lot of TLB entries and page table entries, correct? So, because so many entries are needed, what will happen is the TLBs will very soon fill up, you will have a large TLB miss rate. You will also have a reasonably high translation overhead, which is why you would like to reduce the translation overhead as much as possible. If you are using a lot of memory, it does make sense to create a page which is larger than 4 KB. Correct? So let us say that you create a 1 MB page or a 2 MB page. Then what will happen is that the entire page can be translated in one go. So you'll realize it's a huge page. And instead of having a translation entry for every 4 KB page in a huge page, you just have one entry for the entire huge page. So the number of entries will reduce. The chances of a TLB miss, etc., will be much lower. And the overhead of translation will come down substantially. The only price you will pay is that if it's a 2 MB page, it may be possible that the entire 2 MB is not being used. So you will have some amount of memory wastage within a page, which is known as internal fragmentation. So internal fragmentation should be avoided. So because of that, huge pages are not useful everywhere. They are also not useful all the time. But for very large pieces of software, they are definitely useful. Now the question is that how large should a huge page be? So for that, we need to actually we need to go back and look at this diagram over here. So if you see, I can make a natural partition. Now the partition is over here. That is why I'm saying a page is 2 to the power 12 bytes, which is 4 KB. I can instead make a partition over here and say that every PMD entry is basically a huge page. In this case, how many bits am I taking out? 21 bits. 2 raised to the power 21 bytes is actually 2 MB. Correct? So if I have a 2 MB huge page, then I don't need the lowest level table. Right? So with the second lowest level table, that will actually point to a huge page and I'm done. So you can see how these sizes naturally align with the design of the page table. So that is also why modern Intel processors have 2 MB huge pages or 1 GB huge pages. 1 GB why? Because this point is 2 to the power 30 bytes, which is 1 GB. So then what you have is you'll have one PUD entry will correspond to a 1 GB huge page. And of course, if you are running a very large piece of software like a database system or something, that would really benefit from having a huge page. All right. And it would really benefit because then the entire space within the page, it can manage on its own. So you can clearly see where these numbers 21 and 30 come. And where do folios come in here? Well, folios come in here because a folio is also 2 to the power k pages, albeit in software. So you can say that a huge page is, let's say, 4 folios. Or a huge page is 1 folio. It all depends on what is the maximum folio size on your OS, but this is a configurable parameter. You can always say huge page is 1 folio if you have configured the system in that manner, right? So huge page is a hardware support and folio is a software support, where the granularity is much more than 4 KB, and this is needed for modern software. So now that we have seen this, let us look at a little bit of the kernel code for actually page translation, and we will see that some interesting engineering hacks are there, right? So every time you feel that the kernel will not surprise us, you will see that these little engineering hacks actually make a lot of difference, especially pointed arithmetic that can make a massive amount of difference in terms of increasing the efficiency of the overall system. So what we have here is, this is page table entry to page frame number. That is very easy. And you go to the page table entry, you go to its PTE, and you convert that to a page frame number. So this is very easy because the page frame number is stored over there. The reverse, which is, let's say, well, the reverse we'll just see in a second, but if you want to go from a physical address to a page frame number, you just right shift it by 12 positions. So you eat up those 12 bits and you get the page frame number. The interesting thing is a page frame number to a struct page, because for every actual physical page, you have a data structure called a struct page, which maintains information related to it. So the question is, given the page frame number, how do I go to the struct page? So we will use this little macro over here, which is, there is a little bit of a trick here. This is your page frame number, this is your page frame number, all right? So the first thing is that you typecast it to unsigned long. That part is done. Now what happens is all your page frame numbers are actually broken down into multiple sections. Because it is possible that you have a stack section, heap section, code. They also may be mapped to different memory devices, as we shall see. So it is a good idea to sort of create a hierarchical paging space where you say that I will have sections and then I'll have pages within a section. So we've also seen that, right? The code section looks very different and is very different in character than, let's say, the stack. Correct? So what you get is you get a pointer to the section from the page frame number. All right, so this can easily be deduced from the address. From the address of the page frame, you can easily deduce which section it is in, and you can get a pointer to the section. Then you find the base address of the section and add the page frame number. That will provide you the address of the struct page. So obviously, all of us know what pointer math looks like. That let us say I have double star x and then I do x plus 3. In reality, I'm adding x plus 24. Right? So that's the way pointer math works, because it looks at the data type of the pointer. And when I'm adding an integer to it, it actually multiplies the integer with the size of the data type. In this case, double is 8 bytes, so you're adding 24. So the unit of this is actually struct page star. Okay. So it depends on how it is configured, and it can be struct page star or struct page, but you get the point. The idea is that the moment I add an offset to a pointer, then actually the offset gets multiplied by whatever the size of the data type it is pointing to. So one may want to argue that, let's say I get the base address of a section which is this point, and assume my page frame number is 100. Then I will add 100 and this will give me the address. So just to make things simple, let us assume that everything is 1 byte, right? A pointer is 1 byte. So it's not 1 byte, but let's just make our life easy. Okay, or let's say that, okay, let's make another assumption. Let's say that the pointer is whatever the unit of this is. And so we will just talk in terms of those units. All right. So let us say that it is 100. So, and the address of the section is, let's say, starting address is A. So the thing is that this will actually not be A plus 100. It will not be A plus 100. The reason being that if it's another section, so you just think that there are n pages. So should I allocate entry for all n pages here? And then if let's say there is another section, should I allocate entries for all n pages? It is possible that maybe only 20 pages are there in this section. But it so happens that the address of those 20 pages are from 60 to 80. Correct? So if they are from 60 to 80, then should I, so then effectively what will happen? That I am at A, and then only in this range, which is 60 to 80, will I have legitimate entries. But the rest of the entries will not be legitimate because they map to other sections, right? And similarly, let's say there is a section B, and the page frame numbers which are a part of section B are only 40 to 50. Then only the 40 to 50 range is what will be used. Anything before it or after it, that will not be used. So how do we do this? So this is where Linux uses a little bit of an arithmetic trick. The arithmetic trick is that whatever is returned, so ultimately what you want 60 to be mapped to the beginning of this region, correct? That is why the arithmetic trick that is used is that the base address of a section that is returned, so let us call it base sec, in this case is actually a minus 60. So you actually return this address. If you return this address and it is known that any page frame number in this section is from 60 to 80, in reality you are accessing only a to a plus 20. Alright. So this means that this section is not the real base address, but it is called a biased pointer. A biased pointer is not a real pointer, but it is essentially the base address minus some sort of an offset. In this case, because I'm interested in 60 to 80, it is base address minus 60. Does that make sense? The idea of a biased pointer and how it is very easily possible to do it using simple pointer arithmetic. So let us keep going. So once we have discussed the process of translation at the page table level, let us discuss the process at the TLB level. So TLB, as you know, is a hardware structure. It stores frequently recently used mappings. A modern TLB structure would have an instruction TLB for code. It would have a data TLB for data, and it would have an L2 TLB where basically if something does not fit at the upper levels, it can naturally flow down to the lower levels. So TLB hit rates are very high, upwards of 99%, and a miss is quite expensive because that would require a page walk. Page walks can be done in hardware, can be done in software. On x86 machines, a TLB is a typical 4 to 16 way set associative cache, and you typically have 2 levels, and each entry along with the translation, which would actually be the physical address, the physical page frame number, it also has your protection bits, right? So it also has all the bits for protection. So when we, let's say, change the user process, so for going from the user process to the kernel or one kernel thread to another kernel thread, there is no need to change the page table nor flush the TLB. But when we are switching the user process, there is a need to actually reload the CR3 register because you have to point to a different page table. In this case, there is a need to flush the TLB also, which is a very expensive operation because in case the older process comes back, it will not find any of its entries, right? But TLB flushing is important from a security perspective and also from a correctness perspective. So if we want to avoid this, in the sense we do not want to flush or remove those entries such that they at least remain alive, what are the options that are available to us? The option that is available is that somehow in each TLB entry, I need to be able to add the process ID. But again, there is a problem. The problem is that the process ID is defined at a software level. It's not a hardware concept. So somehow I have to create some hardware concept such that it aligns with a process ID the same way huge pages, which is a hardware concept, was aligning with the notion of a folio. Right. So in this case, what I can do is that I need not flush. Whenever the process terminates, I can selectively flush all of those entries which are part of the terminated process. So I can do a selective cleanup. All right. So a selective cleaning up is possible. And this will slightly increase the hardware overheads because when I am going through the TLB, I will have to match both the virtual address as well as the process ID or some proxy of it, right? So essentially the TLB entry now becomes some sort of an ID. It's actually called the address space identifier, ASID. And then you have your virtual address. So I actually need to match both. Whenever I match both, I get the physical page frame number, right? So yes, it does it does have some amount of hardware overhead. Linux supports ASIDs at the software level, and Intel supports what is called the processor context ID or PCID at the hardware level. So it is possible to associate 6 processor contexts, basically meaning support for 6 PIDs at the core level on an Intel machine. So then what will happen is that for any memory address, the ID will be known. It will be known that let's say it's 6, right? So for the PCIDs, it can be between 0 to 5. So it will be known that let's say PCID 3 is running. In fact, this information is stored in the CR3 register, which PCID is running. And then this information will be used to access your TLB, access the TLB entries. So this will solve some of these problems, so there is no need to flush, and also a selective cleanup, a more targeted cleanup can be done. So the strange part is that Linux actually supports 4096 address space IDs, but Intel supports only 6 PCIDs per CPU, which is fine. If we do not have a lot of processes or many large processes, this idea will work. And so basically the PCID bits are set to some number in this range, and it defaults to 6 on Intel machines, and it is defined in this header file. And so as I just said, that every memory access has to check the virtual address now in the TLB as well as the PCID, which means that this is because 2 processes can have the same virtual address, but because now they are tagged with something which is a proxy for the PID, the translation is going to be correct. And furthermore, to invalidate entries, you need 2 instructions. One is invalidate all, completely disregarding which page is belonging to which process. The other is that you invalidate a subset of mappings, those mappings that belong to a certain process. Let's say that a process is being killed, then we will just invalidate all the mappings that correspond to the killed process. So there is something that we need to look at, which is the consistency, the coherence among TLBs. So let us say that a given page is unmapped, in the sense that I have a multi-threaded program where I have multiple CPUs. They are all running different threads that are a part of the same multi-threaded process, which means that they share their virtual address space. Imagine that one virtual to physical mapping in this TLB was invalidated, which means that this virtual page does not exist. This information has to be relayed to the rest of the course such that they also remove this mapping from their TLBs. Correct? If they are using PCIDs, well and good, then they can do a targeted removal. If they are not using PCIDs, they will either something more has to be done. We'll have to see what has to be done, but at least the space of options is open to us. So let us assume that one of the CPUs, so this invalidation is actually correct, but one of the CPUs over here may be running a kernel thread, or maybe actually running some other process. So the fact is that do you have to invalidate it immediately? In the sense, just because you invalidated a virtual page on some CPU, do all the other CPUs have to stop whatever they are doing, which may be the case that they are doing something else, and invalidate the entry that you want to get invalidated? Is showing that much of urgency actually required, right? Showing that much of urgency is not required, especially if you are doing other work. You can let that other work, which may be more urgent, to actually finish. All right. So this is why you have the lazy TLB mode, where you do not invalidate immediately, and you actually wait for the other work to finish, and at an opportune moment, you do the invalidation. So there are 3 cases. The first case is that, so let's look at cases where the same another thread of the same multi-threaded process is not running. So the kernel knows what is running on which core. So let's say that if another core is running a thread belonging to the same multi-threaded process, then an IPI has to be sent and an invalidation has to be done over there. If it is running some other process or it is running the kernel, then we can wait. If it is running some other user process, it's going to come to the kernel sometime. Then we will see. If it is running the kernel also, we can wait. So let's focus on what the kernel will do when it gets control. There are three cases. The first case is that the kernel does its own work and then it tries to access the invalidated page which is in user space. So how will this happen? The kernel just cannot access an invalidated page in user space just like that. There are no interfaces or entry points via which the kernel accesses, meaning that whenever you access a user page, there are only two functions, copy from user and copy to user. That is how the kernel will access some page in the user space. These functions, copy from and copy to, can be overloaded to check if there is any deferred invalidation work. If there is any deferred invalidation work, then those pages can be invalidated at that point of time. Correct? And then the access can go through. The other is if the kernel switches to another user process. In this case, in any way, all the pages of the original process are flushed out, which means the invalidated page will also get flushed out. See, everything is going, why should I do it separately? Let it all go together. What's the issue? If the kernel is switching back to the same user process, then just before switching back, you see if there is any pending work, right? And if you would recall, there is a complex 5-stage process of switching back to a user process. In one of those stages, you see if there is any pending user work. If there is, which means that a page has to be invalidated, at that point you do it, which means that we are deferring the work of maintaining coherence across TLBs to a more opportune moment where you have time available with you. There is no need to stop a critical task for this purpose. All right. So the last thing that we will look at before we get into more complicated topics like reverse mapping and so on are the notion of how is physical memory managed, right? Because we are now getting into physical memory management, and that this will sort of be like our tone henceforth. So we will look at physical memory, reverse mapping, replacement algorithms, so on and so forth. And the main idea will be that we will kind of get more into the physical side of things. So what happens is that when you have a lot of memory and a lot of CPUs also, the CPUs tend to be divided into clusters. And not all the memory is equally close to a set of CPUs. It is very well possible that some memory is close to, a little bit of memory is close to this CPU, some memory is close to this CPU. So this is a non-uniform memory access machine, where given the fact that you have clusters of cores, CPUs, you will also have clusters of memory, and there will be different levels of proximity. In the sense, this is very close, but this is quite far. So on such NUMA machines, it is important to organize memory differently, such that the notion of proximity comes in, such that the OS knows that if, let's say, given cluster is accessing this set of pages frequently, I will place this much of memory close to this CPU. So this is why all the physical memory is not the same. If you consider any NUMA node, then there is a need to, from its point of view, to partition the entire physical memory space into zones. And then the pages in each zone have to be treated differently. All right. Furthermore, it is possible that some zones may be dedicated for DMA, some may be dedicated for IO access, some may just be memory that is there on, let's say, an NVM or flash or USB or something. So clearly they need to be treated differently. So what we have seen earlier is that there was a one-to-one mapping between the page frame number and a struct page. And this mapping was being done via a section and biased pointers. That is what we had seen. Correct? So what happens is that these sections are very useful if you look at the concept of a zone. So a zone is a chunk of physical memory which shares some degree of commonality, and it is quite different from other zones. For example, you can say that all I/O devices will actually read and write their data from this memory zone. Fair enough. You may want to further subdivide that zone into, let's say, one set of physical pages for I/O access to the printer, one set of physical pages for I/O access to the disk. This is a standard kernel pattern that we have been seeing, which is hierarchical design. Correct? From, let's say, the earliest chapters, we looked at processes and namespaces. So we saw that the entire set of processes are divided into namespaces, and every process belongs to a point in the hierarchical tree of namespaces. Right? So everywhere we have been seeing, and we also saw the same with IRQ domains, that there is a hierarchy of IRQ domains. So everywhere in the kernel, the standard pattern is you make a tree. In this case, in the case of a zone, you divide a zone into sections. And basically what happens is that a set of pages are assigned to a section, a set of contiguous pages are assigned to a section, and then the mapping is done using bias pointers, as we have seen. So making it a section has advantages in the sense you can apply a common policy to all those pages, correct? And you can also evict all of those pages. Those pages can be moved from one physical device to another. So grouping always has its benefits. So if I look at the types of zones that are normally defined, you'll have a DMA zone, which is for DMA access, a normal zone, which is for regular pages. Zone high mem is slightly interesting. This is purely for embedded devices where the size of the physical address space is larger than the size of the virtual address space. Assume it's a 16-bit system. The size of the virtual address space maximum is 2 to the power 16 bytes, which is not much, 64 KB. Or consider a 32-bit system. So the maximum size is 4 GB, but you would have more memory than that. So the physical pages which are currently unmapped or unmappable to the virtual address space because of this mismatch, they are put in zone high mem. For them to get mapped, again something has to be unmapped such that they can be mapped. Then zone movable. Here the idea is that you are assuming that they are on some sort of a plug and play device that you can insert and remove and so on. So it is a known thing that these pages will continue to move or be inaccessible throughout their lifetime, right? So this is zone movable. And zone device is nowadays being used for non-volatile memory devices, where because non-volatile memory devices are somewhere between a memory device and a storage device. So if they are used as storage, they expand the capacity of the hard disk. If they are used as memory, which they can, they are expanding the capacity of the physical memory, right? So they have a dual use. So if they are increasing the memory size and they are not being involved, they still can be involved in storage. But if their primary load is to expand the memory size, then their pages are put in zone device. See, if I look at a struct zone, then this is what it is going to look like. That every zone is assigned to a NUMA node, right? See, there are multiple NUMA nodes. A zone is assigned to a NUMA node. It has this PG list data, which has data regarding the zone. It has a starting page frame number. So we need to understand that all the pages in a zone are normally contiguous, but they need not be contiguous. They can be non-contiguous as well, which is why we divide them into sections. So these three basically say that, how many, present is how many pages are there. Span is how large is the zone from end to the start. being fully aware that not all the pages in the span may be a part of the zone because it is not necessarily contiguous. Then a zone has a name and it has a free list of free regions, which is like a list of holes. So we will see this being used heavily when we discuss the buddy allocator. But the key idea is that if you would recall the base limit scheme, what did we do there? We allocated memory and then there were these holes between allocated regions. This is something like that. So we will discuss this when we discuss kernel memory allocation. But kindly keep this in mind. To manage the memory in the zone, the PG list data structure is used. The data structure here is interesting. So the first thing is that zones themselves are managed hierarchically in a zone tree. So this basically has pointers to all the zones and the tree of zones because it's an entire tree and everybody needs to know who's there. And as I said, present pages is a number of pages that are there in the zone, and spanned pages is essentially end minus start plus 1, right? But that is assuming present will be equal to spanned if it is a contiguous zone. Otherwise, it will not be equal. We will look at these two special entities in the next section actually. So what happens is that continuously a thread keeps running called kswapd. It's a daemon thread whose job is to identify pages in a zone and proactively push them to the storage device to free up physical memory space. So we will discuss this, but remember this. And for storing all replacement related LRU information, the LRU vec is used. So we'll use these two extensively in the next few lectures. So this finishes our discussion on the high level virtual and physical address space management in the kernel. So now we will discuss two specific things. One is reverse mapping and the other is the page replacement algorithm. Then we'll have a very short section which is on kernel memory allocation, which is over here.